Okay, so now we're going to use what we know about free body diagrams and breaking forces into the components to apply that to a situation, and in which we can predict the motion of an object just based on the forces that are being applied to it. So let's check this one out. An 8-kilogram object is sliding down a 35-degree incline, so it's moving. If there's no friction, what is the acceleration of the box? So this is a two-part problem. So first with no friction, and secondly with friction. So as we learned in the last lesson, we got these 5 steps here. We're going to draw a free body diagram, find the components, redraw it, and then sum all the forces. And then we'll see we can predict the motion of this. So first things first is to draw a free body diagram. So what I'm going to do actually is, on this picture we have here, just consider all the forces that are acting on it. So we have a mass here, and of course that mass is going to be pulled straight down by the force of gravity. So we have the force of gravity here. We know that since it's on a surface, we're going to have a normal force. The normal force is going to be perpendicular to that surface. So it's a push perpendicular to the surface on which we're resting. Is there any other force? It doesn't say that there's an applied force, so nothing's going to be applied this way. We just have gravity working on it. Is there a resistance force at all? There's no friction in this first situation, so this is all we have. All we have is the normal force pushing up and the force of gravity pushing down. So one thing that I like to do is actually make the normal force push straight up. So since it's right here at a 35-degree angle, I'm going to push that 35 degrees up so that the normal force is actually acting straight up. So here's the normal force straight up, and that means that this guy's going to slide 35 degrees this way. I brought him 35 degrees down, that means this is going 35 degrees over. So I now have a situation where the force of gravity is actually pushing off to 35 degrees to the right here. The reason I like to do that is because now our surface is flat, and it'll be clear. That makes it more clear. Here's our surface, the box is on it, and here's the way it can move. We've got our vertical forces and our horizontal forces. So second step is to find the components of the diagonal forces. In this case, that is the force of gravity here. Now that we've turned the normal force up, we can find the components here. So we know we have a vertical component here. We'll call that F sub y, F sub g sub y, but we'll just call it F sub y for simplicity. And we have this horizontal component here, F sub x. Of course, these make up F sub g, so you can call it F sub g sub y, F sub g sub x if you feel like it, but for simplicity, since this is the only diagonal force, I'm just going to use F sub x and F sub y. Alright, well, let's break it down. So remember, when we're using our trigonomic identities, only things we have to worry about here are so and ka. So if I'm going to find the opposite side, that is using the sign. So I can say that F sub x is the force times the sine of 35. Okay, there's a problem here. I don't have the force. What is the magnitude of this force? Well, that's the force of gravity acting upon this object right here. So we know that the force of gravity is the weight, which is just the mass times the acceleration due to gravity. So I have an 8-kilogram object, and I need to multiply that by 9.81 meters per second squared, which is the force of gravity in the surface of the Earth, the acceleration due to gravity. So we have 8 times 9.81, which is 78.48. That's a weight, so it's in newtons. All right, we can plug that in over here. This is something you can plug into your calculator. Just make sure that we're on degrees and not radians. And that gives us about 45.01 newtons. So that is our F sub x. That is our horizontal force from gravity. If I want to find the y, F sub y, that is the adjacent side, I can use this exact same thing except flip it on over to cosine. So again, you can just hit second enter if you're using a graphing calculator. That'll bring up the last thing you wrote, and you can just scroll on over and change sine to cosine. Nice and easy. And that gives us about 64.29 newtons for the vertical force of gravity here. Okay, now we have to redraw the free body diagram, and we'll use these components instead of this diagonal force. Let's do that. Okay, so I've redrawn it. We know that the normal force goes straight up. The vertical force, now that we've broken it into its components, is going to have a vertical force here of 64.29 and a horizontal force of 45.01. We're missing one thing. What is the normal force? A lot of people want to tell me, well, it's just the weight. It's the weight. I've always used that, right? We find the weight, and that's the normal force. Not in this case, because the weight is pushing directly down. The normal force is pushing the perpendicular from the surface. So it's not equal to the weight, the force of gravity here. It's not. We've broken this force of gravity into a horizontal and a vertical. And you have to ask yourself, is there any vertical motion? Now that this we're considering the normal force straight up, then that means we're considering F sub g sub y pushing straight down here. So this is our vertical axis. Is there any motion vertically? I'm sliding down here, but is there any motion vertically? No, there's not. What does that mean? That means that this is a balanced force. You can see I drew them balanced. They're the same length. This has to be a balanced force. Your normal force has to be the same as the vertical force because it's balanced. It's not moving vertically. This is unbalanced, so we have some motion this way. But this is balanced. We're not moving vertically. Okay, so it's just asking us if there's no friction, there's nothing pushing back this way. We're free to just push with 45.01 newtons. What's the acceleration of the box? Well, that's easy because I know that force equals the mass times the acceleration, and I have two of those things. I have 45.01 is the force that's acting this direction, and I have the mass, which is 8 kilograms. I can find the acceleration by just dividing both sides by 8. The acceleration in this case is about 5.63 meters per second squared. Hooray, that's the acceleration if there is no friction. Okay, but the second part asks us if there is a coefficient of kinetic friction, this is kinetic friction since we're moving, of 0.25, what's the acceleration of the box? How's that going to change my free body diagram? Well, looking back here at our original, we have the normal force pushing up, the force of gravity pushing down. What does friction do? Friction is a resistance force. It's going to hold us straight up this box. This would be the friction force here, holding us back up that way. So that is just going to add on a force of friction over here. Who knows the magnitude of it? I don't know yet, but when we figure it out, we can actually adjust this. Luckily, this is a horizontal force. Since we've already turned so that the normal force is straight up, this friction force is a horizontal force, straight back this way. So we don't have to resolve any components or anything like that. We can just get right to it. This isn't tough to find because we have the force of friction formula. That is the coefficient of kinetic friction times the normal force. Well, we have this information. We have the coefficient and we have the normal force, so easy. So the coefficient of kinetic friction is 0.25. The normal force is 64.29. When we multiply those, we get about 16.07 newtons. This is a force, it's in newtons. 16, so I'm going to redraw this because it should be a little smaller. Remember, your free body diagrams need to be relative to each other in terms of the forces, how long they are. So if this is 45, I'm feeling this is around 16. Force of friction is 16.07 newtons. Okay, what's the acceleration of the box then? Well, before, when we're finding the acceleration, we only had one force going this direction. And so we said, okay, we got this full 45.01 newtons pushing in that direction. We can find that acceleration from there. But now we have something working against it. So what we have to do then is sum the x's. So if we have 45.01 to the right, and then we have 16.07 to the left, those are opposite directions, so they have to be opposite signs. This is going to be a negative 16.07 newtons. So 45.01 minus 16.07 is 28.94 newtons to the right. So that's a net force. That is our net x. That is the net force in the horizontal direction. So we have a net of 28.94 this direction. Okay, so all we have to do then is find the acceleration using that force. Force equals mass times acceleration. And we know that the force is 28.94. The mass is 8. Divide both sides by 8. And the acceleration is about 3.62 meters per second squared, which is, of course, and obviously slower than when there's no friction. If you got an acceleration that's higher, now that there's friction, you messed up. So this is a rather simple example. There's only one diagonal force. In the future, you might have multiple diagonal forces. Say someone was, we got the force of gravity pulling down like this, but say we've got a rope here and someone is pulling with that rope in this direction because they're tall or something. They're pulling up. Well, I've got two diagonal forces. All that's going to happen is when you break this into components, you're going to have multiple ups. So I might have multiple up forces. I'm also going to have multiple over forces. So your free body diagram is just going to have multiple arrows in the same direction. That's okay. You just have to, at the end, sum them up. You want to find the net force in the horizontal direction, the net force in the vertical direction, and then you can go from there making predictions about the motion.